Okay, guys, welcome to our next live stream session. I'm glad to see that there was a lot of fantastic work on the homework over the weekend, and that I saw a lot of good progress. I'm really pleased about the distribution of marks I saw on the quiz. So I think that people are really, by and large, really getting this material very well, which is good to see. It should all mostly be a review from your organic chemistry, um, so. And so I'm glad to see that it wasn't too much of a challenge for most of you. Like the distribution on the course on the quiz marks really good. We do have enough time here. The quiz doesn't end until the end of the day today, so if you guys want to continue to work on it, that's fine. And I can cover some more material here to talk about some of those mechanisms. It's good to know these things because they're going to be a really important part of understanding when we go through the mechanisms of glycolysis here in the next lecture, to understand the arrow pushing, understand the logic. And this is really cool stuff because when you know these reactions well, you'll be able to predict from first principles why glycolysis, the TCA cycle, and most of the reactions, things that you've never seen before, why they work the way they do. So I think today we can cover a few more examples, and I hope that that will help everybody work through the challenges that they're encountering. Looks like we got a lot of good suggestions here. Ugliness has been contained. And so the structure, though, or the reaction mechanism that we drew is the same as the one I had a second ago here, where the whole hydride, so the electrons and the protons, are still going to this electronegative atom here, the carbonyl, adding to a proton, and that's resulting in this lactate structure here, where the hydride that's added is right there. That came from NADH. Everybody happy now? Next question.
Regarding ring closure reactions for carbohydrates.
Ring closure, sure. Let's do that. So open chain. So we start with, say, I don't know, glucose. 1, 2, 3, 4, 5, 6. Let's see, what is it? Right, 1. Oh no, that's an aldehyde, not a carboxylic acid. 1, 2, 3, 4, 5, 6. So the ring closing reactions here, or actually, you know what? Let's use the structures that we were doing from our examples from last week. The nicely drawn ones here. Where did that go? Not that one. Let's go to these really nicely drawn structures that Carly had. Let's see. We had this example here. Where's our aldolase example? Where's our aldolase example? We did this additional elimination. This is nice. Oh, is there? Oh, here it is. Great. So, so in this particular case, we can just take this guy right here. Let me erase our errors from before. So ring opening you saw before was the abstraction of the base, or abstraction of the not base, but the hydrogen from this alcohol group right here. Well, if you want to reclose it, it's just the same thing in reverse, where you take, the electrons here from whichever carbon you're closing it to. In this particular case, it's this guy right here, and those get added right to there, going to a proton, and that will convert you right back in reverse. Does that make sense? Ring closure. Other questions? Does that answer everybody's question for closing? So
For more reduced or oxidized, when it's a ring structure, would the structure that has more electron interference be more reduced or oxidized?
to tell whether something is more, whether carbon is more or less oxidized, you have to count up the number of substituent, none of the bonds, and you have to add, you have to decide whether they're more or less electronegative. So more bonds to things that are more electronegative means more oxidized, right? That's the, and then fewer bonds to things that are electronegative means reduced. So if you have a double bond and then it's converted into like a double bond to oxygen, and it's converted into a single bond to oxygen with an extra hydrogen, that is reduced relative to the original molecule. Does that make sense? You want me to draw that? I can draw that if that's helpful. Oops, wrong. I think notebook 7 is where we had this notes going. So for example, if you had, go back to our lactate or pyruvate example, you've got carbic, and we'll put the, so this is the pyruvate example. In this particular case, if you count it up, you look at just that carbon, let's just look at that carbon, it's got 2 bonds to an oxygen, 1 bond to a carbon, another bond to a carbon, right? And this R and R, and you're taking it, we want to add up how many bonds to electronegative things. So the redox state here is 0 because it's these are the same level of electronegativity, but in this case it's got 2 bonds to an oxygen, so it's -2 in that case. And in this particular case, we've got when you convert it into a lactate, these are still CR, except we have 1 bond to an oxygen and 1 bond to a hydrogen. So in that particular case, we have -1, right? Does that make sense? The hydrogen is less electronegative than the oxygen. So we have, in effect, we've gone from a -2 to a -1 state. So we have reduced it. Reduction is gain of electrons, right? From the oil rig, you guys remember this, oxidation is loss of electrons, reduction is gain. So that's oil rig is the acronym.
What if there's the same number of bonds differing only in the position of alcohols?
So if you're talking with respect to an entire molecule, and if the isomers are not oxidized or reduced. So these 2 structures here, you can have a particular position that can be oxidized or reduced, but if you're talking about individual molecules, what is this molecule, chat? What is that? Glucose, good, yes. And what is this molecule, chat? Other than ugly. Fructose, yeah. So the 2 molecules have the same structures. They're both C6H12O6, and neither of them is oxidized relative to the other one.
Someone wants to go over how to tell which molecule is most planar.
How to tell which one is most planar? Well, that has to do with the types of bonds. So a carbon that has 4 bonds on it. So carbon with 4 bonds, H, I guess. This guy has a tetrahydrohedral intermediate, so it's shaped like a, I don't know how to draw this in 3 dimensions. It's like a cube. Yeah, something like that. It fills up this space three-dimensionally. It's like a, it's like a pyramid shape where the bottom legs of the pyramid stick down a little further. So this thing is a three-dimensional shape. But when you have a double bond, say a carbon-oxygen, for a carbonyl, this guy is actually flat. Okay. This guy is, it's just flat. It just takes up a flat plane. So anything with a double bond can't rotate, doesn't have free rotation about that bond. It holds the molecules in that attached to that carbon in a flat plane.
What if it's carbon with the same number of bonds, different only in charge? How does that affect the planar state?
What if it's, sorry, say again?
What if it's a carbon with the same number of bonds, differing only in charge?
That doesn't affect it. So, the charge state of the carbon doesn't affect whether it's, is this talking about we have one quiz question where the carbon had a lone pair of electrons on it?
Yeah.
Yeah. So, yeah, right. So, and it's whether the charge state isn't so much it. It's like, so we had, I think one of the quiz questions had a couple of cases like this, or it had a case where we had a lone pair of electrons on there. Okay, so the lone pair of electrons, they stick off in this little sp orbital, or I'm sorry, not sp orbital, p orbital, I think. So they stick off into space and they take up some room, and so that makes this molecule like this. Although this is actually going to have, it'll take up less room and it'll be more flat than it would be if it had a full bond sticking out in the other direction, and that's because this little electron density here sticking off just doesn't stick up as far as a full bond to another atom here. If this were a hydrogen sitting there, yeah. So if you have electrons, the electrons do take up space. Okay. Next chat question.
So when a question is asking about the cyclic structure of a monosaccharide, such as fructose, should we assume a 6-membered ring is being formed, not a 5-membered ring?
So, sorry, say that one more time.
When a question is asking about the cyclic structure of a monosaccharide,
Yeah.
Such as fructose, should we assume a 6-membered ring is being formed, not a 5-membered ring?
Well, whether it's forming a, and for biochemistry examples here, it's the position of the double bond that's really influencing whether it becomes a 6 or a 5-member ring. So when it's on the, for the things that we're talking about, when you see an aldehyde, and we have the, our right, left, right. Oops, this is our glucose, right? Right, let me see, did I get that right? 1, 2, 3, 4, 5, nope. Then, it has 1 at the end. OH, right? 1, 2, 3, 4, 5, 6. Yes. So when you have an aldehyde form here, it ends up forming that 6-member ring that becomes glucose. Where this is the right, down, up, down, down. Let's make this a little cleaner. OH. So when the aldehyde is on the end, that's what it forms. But when it's fructose, it forms the 5-member ring here when this is an aldehyde, or when this bond position is has been moved, and you have you move the double bond from the carbon 1 to the carbon 2 position, and that's how you end up forming fructose, is moving the bond from that number 1 to the number 2 position, right? That ultimately becomes this molecule. Does that make sense, chat? These are the most thermally stable versions of these molecules. And they're the ones that form in, they're the ones that we're forming.
So is it possible to have the pyranose form of fructose?
Is it possible to have the pyranose form? Yeah, with this guy. Is it technically possible? Yeah, probably. But these reactions are forming in enzymes, so it's really. So let me answer in two ways. So first off, so the pyranose is the 6-member ring. Furanose is the 5-member ring. The question is, can it ever close with the 6-member form? If you were doing an open solution, yeah, it could close that way, but it closes that way a lot slower than the 5-member rings. So 5-member rings in regular organic chemistry, those are always the fastest forming, but the least stable reaction. So that's from the organic chemistry view. But in the biochemistry, the reactions are being catalyzed by enzymes. And so which isoform they form is dependent on the shape of the enzyme. So they don't really have a choice in how they form up. Like, when we have the bond there at the 2 position, like it always forms the furanose form. Okay.
So in a shift-based reaction of fructose 1,6-bisphosphate, would carbon 2 be electrophilic?
In a shift-based reaction with which now?
Of fructose 1,6-bisphosphate, so the aldolase reaction.
You want to go over aldolase. Okay.
He wants to know if this carbon 2 would be electrophilic.
Okay, I got to go back and look at that structure. So, oops, that's not what I want. Here we go. Aldolase example again. So whoever's asking, we're talking about the question is about this structure here, whether the carbon is electrophilic or the carbonyl is. Is that the question? Yes, the carbonyl is electrophilic. Yeah, and let me explain that a little more here. So carbonyls are always electrophilic, and the reason they're electrophilic is because of resonance, right? Because resonance, we have R.
Oh, I think they meant like in the ring structure. Is it electrophilic still, or without the carbon?
Okay. Let me finish what I'm saying here, and we'll go back and check. So the reason this guy is electrophilic is that you have a very, very minor resonance form that doesn't really exist ever on its own, where you have this with R. This is R. Gosh, those are ugly. R, where you have this minor resonance form, where it looks like this. So that's one way of thinking about it. Or the other way of thinking about it is just that the oxygen here is more electronegative, and so it's pulling this electron density up towards the up towards the oxygen, and that makes this sort of net delta negative charge in the towards the oxygen. Does that make sense? Okay, so sounds like there was additional questions about this structure. What was it?
I think the question was in the ring form.
In the ring form.
Fructose 1,6-bisphosphate.
Uh-huh.
But carbon 2 still electrophilic.
In the ring form. In the ring form, is this electrophilic? Yeah. Is that an electrophile? And the answer is no, it is not. You have to open the ring before it can be electrophilic. Next.
So someone wants to go over the mechanism for keto-enol tautomerization.
Okay. Keto-enol tautomerization. I think we had a example of that in your structure set, didn't you?
Yes.
Where did?
Aldol cleavage of the aldolase reaction.
Oh, is it? Okay. Aldol cleavage. Like this one here?
Another slide back.
This one here? Okay.
Yes, and it should be with DHAP after GAP leaves that molecule.
Mm-hmm. After GAP. Oh, this guy right here. You want to just do this, that conversion right there?
Yeah.
Okay. Righty. Well, let me just redraw that here. We have, let me just redraw this, this form here a little flatter. So we have a bond here with one side where we got a O phosphate on that side, and on the same side of the molecule you'll have a hydroxyl, and on the other side you have a bond that is got your hydroxyl here. So the keto-enol tautomerization is just an abstraction of this proton here. When it does, these electrons resonate to here, and then these guys go out and pick up a hydrogen from water, or from, this could also be a hydrogen from the base, and then you end up with this form here, O phosphate, and then OH, and then with the new hydrogen there. Make sense? Keto-enol tautomerization. Those move back and forth very fast. They're actually in equilibrium. Other examples or other questions?
One question from earlier. Could you also explain how we can have two reactions at once? Like if it's addition elimination, can we also have an SN2? How can we tell how they're going to react? So I think she means between addition elimination and SN2, can you have the two reactions at once?
Additionally, oh yeah, let's talk a little bit more about this, the additional eliminations versus SN2. I think we had a number of questions that are basically on this topic, and let me just do those more briefly. So quickly, the additional elimination. All right, first, SN2 is a reaction. Frequently we see this in organic chemistry. It looks like this, where you have, I don't know, bromine. This is the organic chemistry version of this, and hydroxyl, right? And a negative charge here, and then the bromine is displaced, making Br minus, right? That's the normal, that's the way you learned it. And so this is a substitution reaction that happens in one step. So these are physically happening at the same time. And what happens in in this particular example is you have a carbon here, and as you recall here, the carbon's got a it's got hydrogen sticking off this side. It's got a bromine sticking off on this side, and the bromine, if you remember your organic chemistry, is, you have this sp3 hybrid bond. It's sticking there. On the far side of the molecule, there's actually this little tiny anti-bonding orbital. And the anti-bonding orbital is where the new bond forms. See, this all seem familiar from your organic chemistry? So what happens is when the hydroxyl attacks here on that anti-bonding orbital side, it can't actually, it kicks off the bromine in the same instant, right? So both the addition of the hydroxyl and the leaving in the bromine are happening physically in the same step. Like there's no intermediate. But when you have an additional elimination reaction, That's not true. There's actually, it has the same net effect. You're replacing one element with another element, but in an additional elimination reaction, say, I don't know, what do we want to do? Let's say we have a phosphate, O minus, this is attached to ADP, right? And we wanted to have a hydrolysis of ADP reaction, say with I don't know, with water. So in this particular case, this would be a normal kind of reaction. Let me actually copy this onto a new page here. Copy. So in this particular example here, the electrons are adding to here. Now, you can simplify this to show this in one step of the phosphate leaving, but of the ADP leaving. But this actually going through an intermediate form that we talked about last time, and that intermediate form looks like this. It goes through a step where the phosphate has that O minus, O minus, O ADP. And you have your, you have your water sticking out there. This is the OH. If this looks like a Texas phosphate, the answer is it has F orbital, so it's allowed to be Texas. So it goes through this form where it goes through this intermediate form, and then it eventually, a base subtracts that proton back off of this guy, and then, then these electrons resonate back down. When they do, they got to kick something off. And it can either kick off the hydroxyl that we just formed and remake water, but that just sort of recycles the reaction. Or what it can do is it can kick off this ADP, right? And so the net effect is that you end up with, a free phosphate, right? Plus an ADP. Right? So we've shown you in biochemistry that you can simplify this whole reaction as, as what we showed up here. Let me just copy this quickly. So we showed you that you can simplify this reaction, show it in one step as a drawing, but it's not actually a one-step reaction. It's we showed that, you can draw it this way for simplicity's sake, and it's frequently shown this way here, where you have electrons coming back, they resonate back down, these guys go out to a proton, and then that ultimately forms this same structure here. There you go. But the difference between this and an SN2 reaction is that's actually happening in two steps, right? It's not that you're adding to an antibonding orbital and at the same time kicking it off. It's you're attacking on the underside of this pi bond here. I guess it's the antibonding side of the pi bond, but like you're going through an intermediate where nothing has been kicked off yet. Does that make sense? That's the difference between additional elimination and SN2. And so if you're adding something to a double bond and replacing it to something else, it will always be additional elimination, not SN2. Seems like that answers the question. Can kinases only add from ATP? I see in the chat. No, actually, there are other kinds of kinases. In fact, E. coli has a mechanism for bringing in glucose. It's called the PTS system, the phosphate transfer system, where it uses phosphoenol pyruvate as the phosphate donor. They're also the polyphosphate can be the source of phosphorus. There are a variety of things that can be contributing to it, but the most common for sure is ATP.
Someone wants to go over enolase and aldolase and what they do.
Enolase and aldolase, yeah. Let's hold that question because enolase and aldolase, we're actually going to go through those mechanisms in detail in the next lecture that I'm about to post. So each of the reaction mechanisms. So let's hold on those questions. But briefly, aldolase cleaves glucose in half. It does that because it's moved the bond because the bond on fructose is at carbon 2, it makes the labile bond right in the middle of glucose. So aldolase cuts it in half, and enolase allows you to make make an ATP. But we'll go through those reactions here in the next lecture. Other questions?
In ornithine transamylase reaction, wouldn't the phosphate be a better electrophile compared to the carbon?
Okay, good question from COSAR on the ornithine reaction. I think that was actually in our homework set, was it, or our example set? So where is that? Ornithine, aldol. Where did it go?
The one,
Is that at the end?
right
here. Okay, so so her question is, wouldn't the COSAR's question is, wouldn't the phosphate be a better electrophile compared to the carbonyl? And you're talking COSAR, your question is here in this first step of the reaction? Yeah, well, I mean, it is the electrophile in the first step of the reaction, right? So the electrons from the terminal nitrogen here, this guy's the nucleophile, and these guys are the that carbonyl. Oh, I see what you mean. These guys out here. No, I mean, so why not phosphate? So to answer her question a little more fully, what she's asking here is that the rest of the structure, I can't really put a box over it and cover it, but you can imagine that this has, let me undo that here. Just ignore that phosphate in there. And imagine it's got this here. And so her question is, shouldn't this guy here be the better electrophile? And so the answer is not really. There are two answers. There's an organic chemistry answer, which is that no, it's not a better electrophile because it's more sterically hindered. But a certain amount of that doesn't matter in biochemistry because what the reactivity is dictated by the enzyme. And so the enzyme is actually holding holding this reaction, like this nitrogen right here is going to be held right next to that carbonyl in the reaction, or in the active side of the enzyme. So it won't have a choice about where it attacks. That's part of how enzymes work, is they really can constrain the chemistry. Looks like we're up on 2 minutes until the end of our live stream here. Any final burning questions that you'd like to have an answer to?
About how many resonance structures does the carboxyl group have?
How many resonance structures does a carboxyl group have? Are you talking about an aldehyde, or are you talking about a carboxylic acid? Carboxylic acids, we'll just do this one quickly. Resonance structures for carboxylic acids. So let's say you have R and you have this structure here. So this guy here has 3 resonance forms. Okay, so this is 1, this is 2, and this is 3. Oops, we got to draw it right. R, O minus, and this plus, with that last one being a non-real form because, exists in very, 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 very minor amounts. But yeah, it does technically have 3 resonance forms. Okay. Yeah, so we're out of time for today. Make sure to check out the material we're posting. I'm just about to upload the glycolysis lecture, the intro to glycolysis lecture. I'll be posting up the next couple of lectures and stuff. You're going to be doing some really cool stuff in your tutorial section this week. So it'll be, that's going to be fun. So check out D2L and good work, guys.